Rascals, and we will be presenting our final detail project, Tornator. We are part of the Mechanical Engineering Robotics track detail project advised by Dr. Doug Eisenberg. My name is Bridget Cochran. I am the team lead for the Riddle Rascals. At this point in time, I'd like to introduce my teammates, starting with Gabe Bentz, Harris Tayeb, Jason Chung, Jaya Wobu, Carl Pushmeyer, Tanner Resnicek, Trent Gardner, and Trent Wargo. Here's a brief overview of what we'll be covering today. I'll take you through a brief introduction of what our project entails. Then we'll go straight into the development, starting with the electrical development and the mechanical, and then then finalizing with the software. Afterwards, I'll take you through a conclusion before we answer any questions you have. To start off, our project name is Tornator. It's a path navigating autonomous differentially driven escort robot. The goal of this project was to create an autonomous robot capable of navigating the Riddle-Prescott campus to accompany students or guests of the campus on their initial tour of the campus. Now we'll take you through the electronics development. We'll start off with the H-bridges, take you through the level shifters, then we'll go through the powering the electronics, power distribution, into the decoders, and also the IMU. For the H-bridges, here's a nice schematic of the signal flow that the H-bridges need in order to function. As you can see, the BeagleBone Black is outputting two signals, a pulse width modulated signal and a direction signal. Those are fed into a customized logic board that opto-isolates the microcontroller and prevents noise and feedback from damaging the microcontroller. Those pulse width modulated signal and direction signals are then converted into two logical outputs. Those two logical outputs are fed into the H-bridge and converted into the control of the motor. Based on the logical outputs, we will either get a positive potential across the motor, spinning it counterclockwise, or a negative potential across the motor, spinning it clockwise. So here's a schematic of the logic board, and as you can see on the table, if the pulse width modulated signal is set to 0, no matter what the direction signal is, we're not getting a logical output whatsoever. However, if the pulse width modulated signal is on, then the direction signal will determine whether or not the logic signal 1 is on or logic signal 2. And as I said before, that just determines which direction the motor is spinning. So, as you can see, we implemented this using inverters and AND gates. And on the bottom of the screen right here, you can see the opto-isolators protecting the microcontroller. This is the layout of our H-bridge. It is the same layout we designed last semester with one major change. These diodes were added in parallel with the resistors right before the MOSFETs. We found out in our preliminary testing that we were getting rather large voltage spikes across our MOSFETs, which was causing them to die off or burn out because they were only rated to handle 60-volt spikes. So we added these diodes in parallel with these resistors to add an alternative current path when we switched directions, which minimized the voltage spike across the MOSFETs. This is the layout of our printed circuit board. As you can see, there are really large traces. The motors that we are working with draw 130 amps on stall, and consistently draw about 10 to 15 amps. So these boards need to be able to handle high current, and as you can see over in the actual implementation, we have rather large heat sinks in place to prevent the MOSFETs from getting too hot. Next, I'll take you through the level shifter. The purpose of the level shifter is to act as a intermediate point between the microcontroller and the power distribution circuit. So the BeagleBone Black will send a ground signal, a 3.3 volt signal, and a 5 volt power supply, as well as a GPIO output that's outputted at 3.3 volts. We use the level shifter to take that 3.3 volt signal and shift it up to 5 volt out. Now, also, we implemented a breakout board, and if the level shifter, for whatever reason, were to break, it's easily replaceable. But one thing that you'll notice is this inverter that we've put in place, and that is because when the microcontroller is powered on, all of the GPIO signals go high. However, when the microcontroller is turning on, it is not ready to receive signals. So we don't want to turn on the power distributor until the microcontroller is ready to receive signals. So when the microcontroller turns on, that 3.3 GPIO is then shifted up to a 5-volt signal, inverted to back down to 0 and outputting 0. However, when we trigger that GPIO down to a 0 low, we are outputting 0 into the inverter, which then outputs a 5-volt supply, turning the power distributor on. Next, I'll hand it off to Trent Wargo to talk about powering the electronics.
Thank you, Bridget. So to start off, we decided that we wanted to use a 2-battery system. First, we used a 12-volt lead-acid battery from Napa, and we also used a smaller 12-volt Jupiter battery. We designated the Napa battery to only run the motors, while we're using the Jupiter battery to run all the other electronics. We did this for 2 reasons. First, we wanted to increase the runtime. Secondly, we determined that having 2 batteries would be safer for the electronics to keep them isolated from the motors. Here's the circuit breaker switch that we used on the Napa battery, and this acts as our pause switch. Whenever this switch is deactivated, the motors are disconnected and they will no longer turn. However, the other electronics still are powered by the Jupiter battery and will continue to run. The Jupiter battery uses this switch here, and this acts as our kill switch. When this switch is depressed, it will turn off all of the electronics. We also installed a 20-amp mini blade inline fuse with the Jupiter battery so that it can protect the electronics if anything would short out. So to go over our power distribution, here's some of the devices that we wanted to power. I'm not going to talk about how we're using these devices, but only how we're going to give them power right now. We had an IMU, a GPS, 2 fans, the Vivo Will and Black microcontroller, the mini box, and 2 encoder-decoder sets. So we needed to use our power distribution for 2 reasons. First, we needed to take our 12-volt battery and regulate that to several different levels for our devices to operate on. Secondly, we needed to be able to turn on and off all the electronic devices that Bridget was talking about whenever the microcontroller is initializing. We were able to switch the devices on and off by using a relay in our circuit. So some of the voltage levels that we required were 3.3 volts, 5 volts, and 12 volts. We were able to achieve these voltage levels by using linear voltage regulators. As you can see here, the input voltage is put onto this pin, and your desired output voltage is on this pin. These are really simple to use because there's only 3 pins on them, and you don't have to complicate your design with a switch and power supply or something like that. So it was really easy to implement these and put them in our design. However, they do come with a drawback. Any excess energy is converted into heat and needs to be dissipated away from the chip. We were able to fix this by adding heat sinks and fans. So here's a quick schematic of the power distribution circuit, and here's the PCB implementation of that. We took that PCB and constructed it here. On this left side, you can see where the 12-volt input signal power is put in. Right here is the signal coming off of the microcontroller that Bridget was just talking about. Up on top, we have our voltage regulator. This board right here is designated as a 12-volt board. I know it's a little upside down there. And down here, this terminal is directly powered by that linear regulator, so that it's always on whenever that's turned on in case you would need something that always needs to be on. These terminals up here are switched on and off with this relay. That's how we're able to turn on and off our devices whenever we need to. Here you can see we constructed 4 of these boards, a 12-volt board, 2 5-volt boards, and a 3.3-volt board. We determined that we needed two 5-volt boards because several devices operate at the 5-volt level, and we wanted to disperse the load of those across two separate boards. Now I'm going to hand it off to Trent Gardner to talk about the decoder.
Good morning, everybody. I'm Trent Gardner. I'll be talking about the decoder, our IMU, and our cape. So, decoder requirements. What they do is they read the gray code that's output from our quadrature encoders. A little overview of gray code. It's just a 2-bit sequence where no more than 1 bit is changing per iteration. So, as an example up there, it goes from 00 to 01 to 11 to 10. The decoder is a state machine. Basically, we're assigning a state to each one of those bit sequences. We're going to track the transitions between those states. And if we know the number of state changes per 360 degrees, which is 500 for the encoders that we have, we can basically count how many rotations our wheels have made and use that to compute our distance. So the decoder implementation was implemented on a PIC 12F629. The state machine was implemented in software via assembly code. 16-bit count register, so that gives us a pretty big area with which we can count. If we go over that, we are going to overflow, but we have the ability to reset if we need to. And we implemented a serial output on this decoder. So I'll talk about the serial output in a little bit. Right now I'm going to talk about how we're powering it. So the PIC can run on either 5 volts or 3.3 volts, which is really convenient. We're running it on 3.3 volts because it eliminates the need for us to put any sort of voltage or level shifting between it and the BeagleBone Black, which would be a two-way connection. Instead, we're just putting a voltage divider on the encoder outputs, which are running on 5 volts, so that we only have to shift it down to 3.3 one way. There's an interrupt on pin 5 coming in from the BeagleBone Black. Basically, when we signal that interrupt, we have a shift register, which is copied from the counting register. We shift out 1 bit of that register at a time per interrupt. So we run 16 interrupts to get the full register. One problem this does bring up is that the shift register and the count register are not necessarily simultaneous. The shift register only refreshes at the end of those 16 interrupts. So if we run those 16 interrupts slow enough, we might have anomalous data coming in. However, that's not really a problem. We can easily run it fast enough. It's just something to keep in mind. There's a reset on pin 7 should we run into problems, say we overflow our count, we're getting bad data. And then we have the inputs coming in on pins 3 and 4 on the PIC. And the outputs are coming in, the outputs coming out on pin 6. So you can see up here, these are the outputs and the inputs from the BeagleBone Black. These are our decoders on the PCB, and these are the inputs from the encoder. I'm also going to talk about the IMU this morning. We're using a Cistern Donner Motion Pack 2. It's not state of the art. You can ask Dr. Bruder about that if you don't believe me. But the nice thing about it was free, so we didn't have to pay $2,000 to get an IMU. We can get acceleration and angular rate data off that. We're operating it off a single 12-volt power supply, which is very convenient because you can just run it right off that battery without having to boost anything up. And we can get an output either over analog channels, which gives us a single channel on the axis, or we can get output off the RS-232 serial interface, which we're actually using to discuss in a little bit. We're going to talk about the cape right now. The PCB designed to sit on top of the BeagleBone. It's actually one of the really features of the BeagleBone is these kind of things. These pins that you can see up here directly to the BeagleBone Black. This is very securely on there, and we can use that to reduce clutter and simplify routing for a lot of cases, especially when you start getting a lot of devices. We can put them on one board, make it really simple. Up here you can see our MAX232 chip, which I'm going to discuss on the next slide. You can see some inputs and outputs. So moving on to that MAX232 chip, I mentioned our RS-232 serial interface, which runs from -12 up to 12 volts. BeagleBone Black's not going to handle that. So what the MAX232 chip does is it actually converts it down to a 5-volt signal level. That's still not good enough for us, so we actually have to put a voltage divider on the data going into the BeagleBone Black before we actually process it. However, the nice thing about this MAX232 chip is that it'll take the 3.3 volt level from the BeagleBone Black and boost it up to RS-232 levels without a problem. I've actually tested it, it works great. On the cable we have additional connections to the PWM and GPIO. The schematic up here is still directly from the manufacturer because we changed nothing on it. It's real nice that we actually had a schematic from the manufacturer that worked perfectly. This is an overview of the whole schematic for the cape. You can see up here, that's the MAX232. Here are the PWMs and GPIOs to the motors. And these are the inputs and outputs of the decoder. And up here you see a lot of grounds because there's a lot of grounds going in. The RS-232 interface for the IMU actually requires 4 different ground points to be connected. So some quick design choices that we made for this. The bottom of the cape is a ground plane, pretty standard choice. Ethernet port restricts the physical size we can build this cape in 1 dimension. If we get any bigger than that, it will start running into the Ethernet port, and we won't be able to plug it into the pin headers. For some reason, the Eagle Auto Router thinks you can route between the pin headers, which you can't, especially not the PCB mill that we have on campus, and which is what we're using to build these. Another thing to keep in mind when you're building capes that we didn't have to consider, but if you're trying to stack more than 1 cape on top of each other, which is very possible to design for, you have to keep in mind the capacitance in those capes, because it can present a problem. I'll now be handing it off to Tanner Resnick to talk about some of the systems.
Thank you, Trent. Very cool stuff. All right, let's look at some actual hardware we got here. Mechanical systems. So we're going to break up our mechanical systems into a couple parts here. We've got our overall fabrication of our platform. We've got our fabulous shell over there. So the platform. Platforms can be broken up into a few assemblies. These assemblies are our chassis. We've got our drive system right here. And we've got our electronics platform. The chassis, the material that we decided to use is a Kevlar Nomex honeycomb composite. We use this for a few reasons. One is that it is provided for us at the machine shop, but I was trying to get rid of it. Another one is it's super light and it is strong. And also it is easy to add new things to it and modify it. And an example of adding new things that we were not expecting, you can see the picture up there on the slides. We have steel supports. As we were starting to put our weights on there, and our batteries weigh quite a bit, our board, our frame started to flex a little bit. So those supports helped keep it from bending. All right, also on our chassis, we made some battery mounts and our mini box mount. The battery mounts are a couple L brackets there that hold the batteries in place, and we have a nylon strap that holds them down. Our mini box mount is just simply 4 different aluminum L brackets standing on end, fitted with foam, and our mini box slides in, fits snugly, and stays in place. All right, our drive system. This was a fun one to design. We can see it right here, and the picture up there is a finished product there. So our drive system is broken up into our motor, our intermediate section, and our wheel. We had to break it up into those few sections as the motors that we do have, Bridget mentioned they pull 130 amps at stall, and they also do not provide a lot of torque. So we had to do this gear train right here to boost up the torque so we can be able to meet our requirement of traversing the steepest slope on campus. All right, our motor is mounted onto square tubing. We wanted to keep it up off the board, as when they're cranking those amps, they like to heat up quite a bit. So the square tubing helps heat sink and keep it up. We also put grooves into it that will tension our chains. All right, and also our drive wheels. Our drive wheels are mounted onto 2 stationary axles here that are welded into place on L brackets, onto L brackets that are bolted into the bottom of our chassis. All right, the last part of our drive system is our intermediate section. Our intermediate section is made of a U-channel that is bolted straight to the chassis. The U-channel has press bearings into it, that a rotating shaft. One part of the rotating shaft is turned down on the lathe so we can install our encoders. The other side has 2 sprockets, a larger sprocket leading back to the motor and a smaller sprocket leading up to the wheels. All right, now our electronics platform. This platform is made out of acrylic, and it houses all the PCBs that our EEs spent a lot of time designing and building. And it has our H bridges, has our logic for those H bridges, our power distributors, and all the other parts that we need to plug in. All right, our H bridges are in sort of a tunnel structure with 2 fans on either side. This really helps with the airflow, and it helps with the power or with the heat dissipation, as those H bridges really do heat up. All right, now I'm going to pass it over to Jason to tell you about our shell sitting right over here.
Thank you, Ted.
So when we originally designed this shell, we designed it as a separate entity from the main chassis of the system so that it could be easily detachable if ever we need to remove it to get into the internal systems. We added in a hatch up in front, which is this gold section right here, in order to access these batteries so that we can charge them or replace them if need be. In the back, which you cannot see, is actually an access panel, which was put in so that if ever there is a need to change the internal systems, we could check and modify and work on the internals right here without actually having to remove the shell, which would be a pretty difficult process. The original design for the robot had a flat top, which was where the interface would reside. Problem was, we decided that having an interface so low to the ground would actually be a lot harder to use and access compared to something that's up at a decent height. So what we did was we raised that back section to about between 35 and 41 inches, so that, which we found to be a pretty good height for anybody of any height to access the panel without having to bend over or work too hard. Now what this podium, is what we called it, houses both the kill and pause switches that will be used for powering or turning off the robot, as well as speakers that will play the audio of the tour or some kind of music while it is moving around campus. Now, the way we created this shell was we used blue insulation foam, and what we did was we cut the foam into individual pieces, as shown here, that will take up the different walls. The only issue was the front portion, which is curved, and we couldn't really cut a curved portion of foam. So what we did was we created a bunch of rectangular pieces and stair-stepped them so that we could, once they were all glued together, we could later sand them down and create this nice, smooth front section. Once all the foam was glued together and cut out and sanded, we covered the foam in fiberglass and 2 coats of resin. The first coat of resin was just resin to harden the fiberglass and allow it to become a little bit more sturdy, whereas the second coat was resin plus microballoons, which made it nice and smooth and made it a lot easier to paint. This wonderful color. I'll now hand it off to Carl Puschmeyer to talk about the software.
Thank you, Jason. The software we'll be going over today is broken up into the control process, the user interface, the networking, the odometry, the controller, the camera vision, and camera calibration. To begin the control process, we selected our MiniBox custom PC because it was available to us, and our Beagle Black microcontroller to be the control components of our system. Those interfacing components to those controllers are our encoder, decoder sets, and our USB video cameras. All programming was conducted in Python 2.7. Our control process begins with user input that selects the current location and the intended destination. With that selection, a point-to-point navigation is then conducted through the control process, where a spline is projected from one point to the next subsequent point, and the controller outputs PWM values, or the duty cycle, to allow the motors to turn and follow that spline along the path. The feedback then translates back with the encoders for the controller to then update the odometry and loop through the system until each point is reached. As the projected spline is followed, the controller also back checks to make sure it is not veering off the path. It does this with the camera vision system to make sure that as it's getting closer to the path edge, it corrects itself to the center of the path and continues along, and then reprojects the spline to the nearest node and continues along that spline until it reaches the node. As a node is reached, it is then checked to back check to see if it is the goal node, and at that point it will either repeat the process or project to the next subsequent node. The user interface was selected to be a drag and touch Y88X touchscreen Android tablet. It was chosen because it is a very cheap tablet, inexpensive, tablet, and it also has a fairly updated Android operating system. This allowed us to use a programming language called Kivy to program an app into the tablet itself. KV is more or less synonymous with Python 2.7, making us able to program in Python 2.7 and then distribute the app over to the tablet using a distributor called Bulldozer, which was developed by the KV community. The app was designed to be a button interface that displayed the current location and the goal location. When selected, networking is established between the BeagleBone Black and the between the mini box and the BeagleBone Black microcontroller. The connection is established via Ethernet and is run on a socket server client. When the process begins on the mini box, the process is also started up on the BeagleBone Black and using that socket server client. Once the connection is established, the control process begins, outputting the duty cycle signals to begin the motor rotations, and then the feedback is received from the BeagleBone Black so that the control process can continue. The pulse width modulation signals were generated in the controller, and the encoder feedback is generated from the 16-bit signal sent from the encoder-decoder sets that's translated into the decimal value, which is accurate representation of the counts on the encoders themselves. This encoder-decoder set was tested with a potentiometer, the BeagleBone Black, and the decoder circuit. The user would then move the potentiometer to a desired orientation, then compare the output on the monitor to see if the translated value is concurrent with the angle on the potentiometer. Once we established that the angle was accurate, we knew that we could accurately display the counts represented by the encoders and update our odometry. And with the odometry, Jai will discuss it.
Odometry is important because without odometry, the robot has no idea where it is. So to start, we had 2 drive wheels. Each of these drive wheels has an encoder attached to its intermediate gear shaft with a gear ratio of 11 to 60. Each of these quadrature encoders have 500 pulses per revolution, and the count from the BeagleBone Black is then converted into physical wheel rotation using the following equations. After these equations are implemented, the position and orientation are then fed into the controller, which I will now discuss. The controller we're using is a backstepping controller with the concept created by R. Fiera and F.L. Lewis. It uses a combination of a kinematic controller and a torque controller using a dynamical extension. The dynamical extension is designed to have 3 major steps. First, the feedback velocity controller inputs are designed to make position error asymptotically stable. Then, a feedback velocity following control law is designed such that the velocities converge to the given velocity inputs. Then, the second control signal is used to compute the required torques for the actual robot. The dynamical extension could also be expressed as a series of equations. To determine that the controller met the requirements for this project, we put the backstepping controller through 3 different tests: a comparison test, a trajectory test, and a parameters test. During the comparison test, we compared the backstepping controller to a PID controller designed in Robotics 2. As you can see, both controllers were able to precisely track the trajectory shown here. But if you look closely, you will see that the backstepping controller was more accurate than the PID controller when tracking trajectories. After multiple comparison tests, we were able to determine that the backstepping controller was more accurate than the PID controller. So then we started our trajectory test to see how the backstepping controller tracked various trajectories. As you can see in the following graphs, the backstepping controller was able to track each trajectory precisely with little to no error. Afterwards, we then performed the parameters test. The purpose of this parameter test was so that the team can have a better understanding of how changes in parameters affects the controller's ability to track trajectories. As you can see on the left, the backstepping controller was able to accurately track this trajectory using a normal K1 gain value of 0.7. The graph to the right shows the controller's ability to track trajectories when we are to double that gain. As you can see in the X direction trajectory at the top of the graph, the controller was unable to correct this positional error. Using these parameter tests, the team now has a better understanding of how to fix issues when the controller cannot accurately track the trajectory. In this case, the team now has a better understanding of how to fix an issue when the controller cannot accurately track the trajectory in the X direction. And now I'll hand it off to Gabe Benz, who will talk about the camera vision of our robot.
Thank you very much, Chad. Well, I'm an ME2, and there's the vision system. The vision system for our robot was designed to perform one basic task, which was a localization algorithm. The localization that it performs is a distance measurement with respect to the robot frame with respect to the edge of the sidewalk. In order to do that, we utilized a single off-the-shelf Logitech webcam, and then we used the OpenCV Python vision library, which is readily available and open source. So, in order to detect the edge of the sidewalk as the robot is moving along, there were a few fundamental assumptions that we had to make. The first was that we were on a flat surface. Within the frame of the camera, we assume that everything is flat so that it makes our calculations for localization a little bit easier and reduces the need for two cameras, assuming a plane. We also assume that the sidewalk edge is flat in the range of the camera. This is useful later on when we are projecting basically a virtual wall along that sidewalk edge. And we also decided to focus only on the right side. Since the sidewalk is symmetrical, you can reliably localize the robot within the center of that sidewalk using only one edge. So, the first step of the system was to actually detect the edge. And right here is a basic image that we started out with using in our lab. The first thing we did to the images as they come in from the video stream is we apply a bilateral filter to them, which is basically a blur. This blur helps to eliminate salt and pepper noise. It's something that's caused very often by gravel and grass, which is quick fluctuations in color and texture and changes that this filter helps to eliminate and smooth out, but still leaving the primary edges that we're looking for intact. We then also applied a grayscale to the image just to, again, reduce computational load by eliminating the three colors. After that, we implemented the canny edge detection algorithm, which works by measuring the differences in intensity over ranges of pixels. From that, we were able to get a general set of points of the major lines in the image. And in order to actually define the final lines in the image, we utilized the Huff transform, which is basically a line fill algorithm that is based on points already on the line. So in this case, we would measure if this line contains 10 points and is of length some L, then we consider it a viable line for edge detection. So, looking at an actual sidewalk edge, we're able to get to the point where we're able to detect the major edges in it. But we also have one other problem, and it's the horizontal lines that can appear in a sidewalk image, the cross lines. So in order to eliminate those, we applied an angle threshold to the lines that could possibly appear in this image, from about 80 to 160 degrees. Within that threshold is one that the robot can actually exist within, but also not detect those horizontal plane lines that are not useful for localization in any way. And then as a final step, in order to eliminate any remaining noise from the gravel on the one side, we performed a minimization of X values in certain Y regions. So the minimum X value in the Y region up to the first green line, and then the minimum X value in the second Y region up to the second Y line. And that would be differentially reduced to what the fidelity we needed. We were able to detect the edge of the sidewalks within an accuracy of 0.5 to 1 inches, which, given the scale of our project, was very good. So, in order to actually determine the real-world distance of the robot from the edge of the sidewalk, we had to do a pixel transformation. In order to do that, we basically did a manual calibration of a given frame. Since the camera is fixed on the robot, we were able to take a single picture and then measure where in the real world, okay, it's never going to work, where in the real world a pixel location appears with respect to the image frame. So you can say, okay, a pixel somewhere in the middle of the image is 3 feet in front, 6 inches to the right, and you're able to create a function that immediately transfers that pixel location into a real-world location with respect to the robot. So, in order to perform the actual localization, Right here, you can see an image frame where we have the side of the sidewalk laid out in a set of points. We then run that through the transformation from our previous calibration and create an edge line that we can project however far we want, assuming that it's a straight line in front or behind of the robot. This is useful because in finding the minimum distance of the robot, since the camera is looking about 3 to 5 feet in front of the robot, we project the sidewalk edge to alongside of the robot using a polyfit system, and then we are able to make distance measurements to points on the line to the frame of the robot. The minimum distance of those is the robot's perpendicular distance from the edge of the sidewalk. From that, we can send it onto the controller and say, you need to get away from the sidewalk, or you can move in closer to the sidewalk. Now to talk about the analytical camera calibration system is Aristotle.
Thanks, Dave. All right, so I'm going to discuss the calibration process of the Tornado's vision system. All right, here we go. So this is our camera model. It's applying the perspective endpoint method. What we did here for the first step was we took a picture of an object or feature in the real world, and then we measured the distance, the total distance, from the object to the camera. Then we pulled the image up on our computer screen and made a relation with the camera frame and the screen coordinates. And from there, we made a relationship of the camera frame to the object in the real world frame. Our calibration code was written in MATLAB, but most of our vision system is designed in Python 2.7, so we had to take in the Python indexing when we had our code generate outputs for the calibration code. The way Python indexing works is the screen origin is at the top left corner of the screen, and the rows of pixels gives the X component of the feature on the image, while the columns of the pixels give us the corresponding Y components. And the camera frame is at the center of the screen. Our code solves for 3 parameters, 3 angular rotations, phi, theta, psi, and the x, y, and z components of the vector r, c, where the magnitude of this vector is just the distance of the camera frame with respect to the robot body frame. So our code applies the Newton-Raphson method. This was done just because of the vector and matrix map. And we ran 10 to 15 iterations and found that it gave us pretty accurate outputs. We also did a test for the orthogonality of our angles, where the angles were used in the transformation matrix CTR, going from the camera matrix to the robot body frame. And once this matrix is multiplied with its transpose, it outputs the identity matrix, meaning that the angles are orthogonal. And now we're just going to wrap it up.
All right, thanks, Harris. Okay, so now I'll take you through a conclusion. To start off, we'll go over just a little bit of our budget. This semester, we had a budget of $8,000, and considering the scale of our project, that was very, very small. However, despite all these purchases for the mechanical system and a lot of electronic components, we were about $40 under budget, which was pretty exciting. That also made us meet our first requirement. Overall, we met 12 out of our 13 requirements. The main requirement that we were not able to meet was getting the robot to be able to traverse the entire Riddle campus. At this point in time, the odometry code is working. However, due to hardware malfunctions, one of our encoders is not giving us correct outputs at this point. So despite our code working and being able to correct itself, it thinks it's spinning in circles right now because the encoder isn't outputting the correct values. So we were not able to meet that last requirement. Otherwise, our robot fits through doors and is able to traverse the tallest slopes on campus, as well as the rest of those requirements. We met all of our electrical and software requirements as far as user interface, ease of access, and software implementation. So at this point in time, the team will stand up and we will answer any questions that you have.
guess I get to go first. First, I just want to congratulate you on the overall great project. I think one of the things that I really enjoyed, at least during the discussion, was that I'm a big believer in multidisciplinary teams. So the fact that you actually had students from different departments all contributing to the same project, I think that's a very good step in the right direction. Having mechanicals such as myself trying to do electrical design is not a good idea, and vice versa. So I think teams that have the benefit of being multidisciplinary actually are an advantage. So I do want to congratulate you on that. Second thing is autonomy is very difficult. So you tackled a tough problem here. It's very challenging, and integration of vision processing and all that is among the most difficult challenges in robotics. Okay, so now with that said, I have a few comments, recommendations, and a couple of questions. I don't want to spend too much time so the other panelists can ask there. So I'll try to limit to like maybe one per subsystem, if that's okay. So overall, one suggestion is, I saw at the end of your conclusions, you provided all the requirements, the overall requirements. And my preference would have been to see the overall requirements up front. Then we have a good idea as you go through each of the subsystems. Subsystems then present their subsystem level requirements. And then when you come back to your conclusion, show, based on testing, analysis, or whatever process you went through, that we met these various requirements. So that's a recommendation that you might want to consider as you go forward into industry. You always want to give your requirements up front. That's very important. Let's see. Electronics. There's a lot of electronics integration on this platform. How do you deal with the planning for malfunctions?
That was actually why there are so many electronics on this platform. As you can see, Trent Wargo over here worked on our power distribution board, and he separated each individual one of those boards so that it would be easier to debug and test if we were getting malfunctions. As far as the H bridges, we separated the H bridges from the logic boards so that if we weren't getting a logical output that was correct, we could eliminate it to just on that board. So we tried to keep our electronics very separate, very spread out, so that it was easier to debug for that reason.
It's just, I guess another kind of general comment is, you always have to plan for the bad day, because it will come. So
We have them.
we'll have many more. So let's see. I guess along those lines too, when you're selecting components, like for example, you pick the big lead-alone black, really low-cost microcontroller. Did you go through an evaluation process of looking at others and doing some sort of comparisons, cost, performance, functionality? What was the reason for selecting that particular?
The biggest reason for selecting that is I personally have familiarity with it when we were picking our microcontrollers. I worked with it before, and really the biggest thing that we picked it for is the sheer number of input-output pins that it provides, and the ease of access with which they have, with which you can use them. Some of the other teams that I've seen, they're using boards with maybe 10 to 15 pins. We have over 50 pins that we can use to do various things, and there's built-in PWM, built-in UART access, there's built-in SPI, which would come handy if we were, say, working with a GPS or some other electronics like that. So the biggest thing for that was the ability to interface with so many different components at the same time in so many different ways.
Okay, very good. Familiarity is important. Let's see, mechanical. There was a couple comments made here, and I wasn't exactly sure what was done about this. So when the chassis was put together and you added your weight, you said weight started, the weight of the batteries and so forth started to flex your chassis. Did you perform any sort of structural analysis before you started adding in like ribbing and so forth?
Yes, so last semester during preliminary design, we designed it with a thicker composite. We were just using what was handy at the machine shop as we're trying to keep the price low.
Okay.
And it happened that he didn't have that thickness anymore, so we went down a little bit, and I did perform an analysis on it last semester.
Okay.
And yeah, I didn't assume, it doesn't flex too much, so it was just right there on the break and working.
Okay, so I think the lesson learned there is design versus build. When your materials change, you've got to reanalyze that situation. Just another suggestion there. You talked about the steepest slope.
Yes.
I don't know exactly what the steepest slope means in terms of something that's quantitative. Is it a 35-degree angle, or what kind of slope are we talking about?
Yep, so last semester we went around to all the different inclines and sidewalks on campus. And we went around measuring all of them, trying to find the steepest one, as that's what's going to require the most torque on our robot, which is going to make the most amps. So we found our steepest slope is 15 degrees on campus, and it's just a short little sidewalk down in the middle of campus. And so we just had to design for it to be able to have enough power to go up that slope.
Okay, so the reason I bring this up is that's probably one of your most important driving requirements.
Yeah.
And steep slope doesn't just affect your drive torque, it also affects your wheel size selection, which then your motor size, and all of that feeds from that steepest slope requirement. So again, I'm getting back to I don't mean to harp on this, but requirements are so important. And when you take a high-level requirement like that and then break it down into its subsystems, you can see how it just proliferates throughout your whole design. So,
yeah, so designing, we did look a lot into that, and I wrote a test document, and after we built it, we took it out there and made sure to do it and saw how it affects the mechanical system.
okay, very good. Let me say a couple more so I can get on, so the other panelists can ask you questions. I guess in the software area, it wasn't clear to me up front, when you go through your trajectory planning, how many degrees of freedom you were planning for until I actually saw the plots and the equations. Briefly saw the equations. I think that's another thing that needs to be emphasized up front is talk about what are you functionally trying to do here? Am I designing a robot that's going to be going straight line trajectories from point A to point B, or do I need a robot to go from point A to point B with this type of orientation? Since it's planar, you know that it can be 3 degrees per max. So kind of figured that's what you were aiming for, but it wasn't clear to me until that portion of the presentation that you were actually getting to, that you're actually planning, your trajectory planning was based for 3 degree freedom planar. So I wasn't following that. That's just, again, something to point out there. I think that's pretty much all the main things that I have. I'm going to talk with you guys out in the hall sometime, just ask you if you really know the details, but I'll pass it on to AJ. Thank you very much. It was very good job.
Thank you for your feedback.
I'm going to reiterate that those were done. I'm not a robotics person, so this is very interesting to me. I learned a lot, so I appreciate that. But that also means that I have some questions. I don't have the familiarity that Wes has. Similar to his question on the chassis structure, but different. How was the weight estimated and tracked throughout the process to ensure that you stayed within the capability of the drive system, particularly when you're talking factoring kind of that steepest slope types of things?
And so last semester in preliminary design again, we went through all the components, and we actually modeled this whole system in using CATIA and giving actual weights for the motors, for the battery, for everything on there, and we could see overall what the weight was. So that's how we estimated what it was going to be. At this moment, because we were building all the way up until this morning, 4 in the morning, we were unable to even grab a scale and see what the overall finished weight is. Yeah, so we designed to it with CATIA last semester.
Okay, it would be interesting to see how close you were.
Yeah, I'm interested too. We have a week of, we're going to go test everything and see.
Good. Okay, good. Battery component selection. Why did you pick 2 different types of batteries? What was the rationale on that?
Well, initially, we knew that one of the batteries was going to have to help drive the motors. And with motors connected to the battery, it creates a lot of noise and feedback. And with a microcontroller, that kind of noise playing off of just the the power system can corrupt it or create false signals. So we wanted to have 2 separate batteries, one to help drive the motors, so that everything connected to that battery could be noisy and wouldn't really be damaging. Whereas the other battery controls just small drive electronics, so that low current, low noise, we're not getting a lot of feedback that could potentially harm them.
Excellent. That was a good answer. Where I was going to go with that was if you have the ability to minimize the part count, then in the overall design of your vehicle, it'll keep your costs down. It just simplifies things, but you had an excellent reason for doing something that drove you away from that part count. So I appreciate that. Great work. That's all I got.
Thank you.
First of all, it's a great project. So ND 520 is the detail design, and there's one prior to that that's agreement.
Yes, so we do 1 semester in preliminary design, which is mostly paperwork and testing and analysis prior to actually compiling the project. This semester was spent taking that design and building.
Cool. My background is in control systems and integration and test. So I've got a couple questions related to that and the software and the vision system. Did you guys do a preliminary hazard analysis or any more detailed hazard analysis on your integrated system, particularly related to the navigation and the guidance part of the vehicle? And if so, what kind of hazards did you identify? And how did you mitigate those hazards?
Carl, would you like to answer this? Okay.
Okay, so by hazards, are you referring to physical hazards or just errors in control method?
Well, like for instance, in aircraft, we're often worried about the vehicle damaging itself, damaging property, or injuring someone. And so we go through a hazard analysis to look at what kind of things could go wrong. So, for instance, you've got a navigation system that looks like it's based on the odometry, and it's got some feedback with the camera system. Did you look at how failure of any of those sensors would potentially affect the robot, and do you have either software or hardware that would, say, prevent the robot from driving off into the weeds and damaging itself, or driving off and hitting a building, or for instance, what if the vision system detected like loss of edge because maybe some object was in the path? You have mitigations for those sort of things. Those are the kind of hazards I'm referring to.
Okay, so because we were pretty much learning as we were building this whole control process, a lot of what we had actually implemented was very basic in its nature. So the odometry, we use those raw signals from the encoders, decode them, and then convert that into the actual odometry. And then we fed that into our control process, subsequently into our control process. That was basically just the raw values, not really taking into account any additional outside influence. So if we had slip of the wheels, it wouldn't recognize that. But that's why we had planned to implement the IMU to account for that kind of mistake in orientation.
Okay.
So it's kind of a back checking thing. We had earlier on the semester, and as part of a previous course, they checked out using a more capable IMU to actually check to make sure that things had stayed on course. For this actual project, though, I know that the output of the IMU wasn't quite accurate enough to implement it into the system. As far as vision goes, we had detection of the sidewalk, but that was more just path correction. It hadn't quite been developed into object detection yet, but we had left that capability open, and we have another mount and set of camera to have that capability in the future.
Okay. Well, you guys have done a lot in the semester. One of the things to consider for as you go out into industry and in your career is is to sit down and ask yourself, okay, what could go wrong, and start at the requirements phase. Ask yourself what could go wrong, and how can I design my system to mitigate those potential hazards. Because if you discover a hazard after it's built, it's a lot more difficult to go back and try to fix that. So you want to do that up front. I saw that you had a GPS unit in your power requirements. I didn't see it integrated into the system. Perhaps you have future capability there. I was wondering if you could talk about that.
Yes. Okay.
So we do have a GPS, the U-Box Cam MAQ. This GPS has actually been successfully used by another detail team this semester. Part of the reason why we picked it is because we were going to work with them on it. We just didn't have the time to get around to it. Basically, we know it's usable. We know how to put it together, how to make the parts for it, how to make a working circuit out of it, and how to get data from it. We just haven't had the time to do it.
Okay, understood. Let's see. On to electrical. One of the things that's pretty common to happen in vehicle integration is, especially when you're dealing with a composite chassis, is a common ground, electrical ground that is. Have you guys had any grounding issues, or did you come across any power problems related to ground?
The biggest grounding issue that we have, so our system is opto-isolated. So the motors and the electronics are running on separate grounds, hence the two separate batteries. However, the only grounding problem that we more recently ran into was with the level shifter. We weren't actually able to figure that out, but we found out that by removing the level shifter and just having the inverter, it was capable of doing exactly what we needed it to. But otherwise, we tried to pay particular attention when we were creating the printed circuit boards that we didn't create ground loops, so that we didn't get different potentials on different sides of the boards. And at this point in time, we haven't had any problems keeping the system auto-isolated.
Well, that kind of extends to the limit of my knowledge of electrical systems. But, mechanical. I notice on the sprocket that's coming off the motor that looks like there's several inches of overhang on the arm. Did you do any analysis to look at overhang loads on the shaft coming out of the motor? Did you have any problems associated with that?
All right. First off, yeah, that drive system was particularly fun to put together. So last semester I did do an ANSYS analysis on that whole intermediate section with the shaft and how big it is. And the deformation wasn't anything significant to cause problems. And at this moment, that overhang, it's there right now, and it probably would be cut off. There's no reason for it there. It just hasn't gotten around to it. As we finish something and it works, let's move on to the next one and make sure it works. So it doesn't cause any problems just from doing analysis on it.
Okay, cool. So that kind of wraps it up for me. I think I would echo the comment on requirements and defining your mission up front when you make a presentation, so that the people reviewing your presentation understand what some of the choices that you make as you're presenting your results in the presentation. But fantastic job. Nice work.
Okay, thank you.
I think you guys chose a very ambitious project. I'm very impressed at the progress you've made, the product you've shown here. So I think you guys did a great job. I was also going to mention something about requirements, but that would just be belaboring the point now. So, sort of off of that, when you showed the requirements at the end, I noticed you had an hour of runtime based on one charge. What system do you have in place to recharge?
We actually have to move it right here. It's just a system that plugs right into the wall. So we removed it just for the sake of beauty this morning.
So right now it's just a field expedient system.
Yes. But it plugs right into the battery, it plugs right into the wall, so you can back it up to a wall plug, easily accessible. That hatch opens up, the cord's long enough to reach, and you just back it up to a wall.
Okay, stepping back a little bit from the technical detail, let me ask more of a 30,000-foot question. What did you take away from this that you're going to carry with you into industry, and what would you pass along in terms of information to the next robotics casting team?
Well, I think all of us have had quite an experience, particularly with integrating everything. I think that there was so much to learn. I can't even start to describe how much there was to learn. Staying on track, trying to follow a schedule was definitely difficult. But also, at the beginning of at the end of last semester, when we did our preliminary design, we had a lot of feedback that this project was very ambitious. There was a lot that you obviously see, including the GPS and IMU, that we weren't able to integrate into the system. And I think trying to eliminate that go fever and say, okay, what is actually feasible, and listen to feedback from people who have experience in this field and understand, this is a lot. And I think that we've all learned that, we should definitely take that advice. But otherwise, integrating the system was a challenge in itself, but communication was definitely key. And I think the team did a really good job of keeping that communication open and making sure that the electrical system was capable of communicating with the mechanical system and making sure all those intermediate steps were followed. As far as feedback to the next group, I think that, like I said, we should follow or listen to our peer or advice from the boards from our preliminary design, because we did take on a very ambitious project. Did anybody else have a comment on that? It's a pretty open question. Okay.
Thank you again. I think you guys did a really good job.
Thank you.
Morning, everyone.
Good morning.
Start with a bit of a quickie top-level question. So when I saw towards the very end, one of the last slides, 12 of the 13 requirements have been met. As an observer, if you will, it would lead me to believe that we're both so close to the finish line. Help me by giving me a little bit of a reality check. What percentage, if you will, of the effort remains? Or if you want to put it in a broader context, how much longer would you continue working at it before you were able to say this is something we can actually deploy?
At this point, we have code working with the odometry. If we could replace one of the encoders, we know that we could get the odometry working between point A and point B. We would have to then spend time mapping out the rest of the campus, so we would have, at this point, a distance between the robotics lab and AC1, able to implement just odometry. It would probably, in my guess, take another month or two to implement the IMU and GPS, but as far as the vision system sits, maybe another couple of weeks if we could get that encoder in place.
I'm going to update that vision, and I would say that the vision system would be ready to go almost a day after the odometry is in.
Okay, so like I said, the 12 of the 13 requirements, our requirements were very broad. I would comment on that. So there were no specifications, or it was not specific as to which sensors we had to implement. So we had planned on implementing the IMU, planned on implementing the GPS, but as it turned out, we've implemented the odometry and gotten the vision system to work. So with that encoder replacement, it would be, like I said, another week or so.
So let me restate the question.
Okay.
So what percentage do you think remains of the overall effort, and how long do you think as a team, if you were, say, to continue, would it take to complete, to get to the point of completion, i.e. integration?
Okay, so to get the IMU GPS, like all of our original plan in, I'd say we're probably sitting around 70% complete. To get the odometry vision system, we're sitting around 95% complete. I think that if we really were ambitious and sticking around for the summer, we could get all of those implemented by the end of the summer.
Okay. So kind of last question to everyone in Knowing now what you do in hindsight, perfect vision, if you were to go back to the beginning, let's say we could rewind time a year prior to where we are now, what would you, I want to hear from everyone, what would you individually, one thing, if you could do one thing differently, what would it be?
I'm going to see what everyone else has to say.
Yeah, you've been doing a lot of talking.
Yes.
So I spent a lot of my time working on the power distributor, and at first I tried to make everything on there one board. And then things got really confusing because there's lines everywhere, I never used equal, and I had to make PCBs. So I took that and I simplified it, and I just made different boards for each voltage level. If I could go back, I would first of all put all those down on the one board. That would save a whole bunch of room. It won't twang around like Dr. Eisenberg likes to play with it. But also I could take that whole thing and I could implement a switching power supply in it, which would be a lot more efficient.
So being in charge of the mechanical system and building it, if I could go back and redo it, I would design a different chassis, not using the, just making something a little bit more sturdy. So just fixing that, and a big thing I took away is just designing something on a computer software and then going in and actually building it. And you see a lot of things don't look the same in real life as it does on CATIA. Spacing looks great, and then in real life, you're like, oh, that's not going to work at all. So just I learned to really how it goes from computer to an actual building.
So being one of the primary people on the software side of things as far as the control system, like not the controller itself, but just integrating all the different components, including the encoders, translating those, sending them over, networking them over to the mini box from the Beagle loan, and making everything work nicely. It would have been real nice to have a couple other people on the project, kind of looking back and forth, looking at stuff. And as we found out early this morning, we had 3 of us working on just checking over the work and testing stuff, looking up stuff as it needed to be checked. It worked. It made really quick progress of what needed to be completed, and we actually got it looping successfully by early this morning. So, so with that said, it would have been really nice to have said individuals working with, having just more than one person working on that code. Maybe not writing it there in step, but checking it back and forth, doing the research on it, learning it so that it wouldn't have to be explained later on, and moving on from there. Of course, it was a little hard to do that because we had so many different tasks being carried out through the semester, but we probably would have trained, if you will, someone to learn all that kind of stuff and have it implemented earlier.
Okay, so if I could go back a year with hindsight, I would probably try to dabble into everyone's section and try to help them out a little bit more. I realized that this project is a big project. There's a lot of opportunities to learn, and I feel like by holding myself into one section of the project, I wasn't really able to get such a good understanding of the electronic system or the design of the chassis and all that. So I feel like if I could go back, I would try to just learn as much as I can about the project and take it from there.
If I could go back to the start, I would probably try to put more effort and more time into working on this, and not just the stable class time or just a few hours outside of our given detail time, but as well as that, start on designing like the shell, which I was the main person on. Probably start on working on that a lot sooner, because I did when I was actually creating, I didn't realize how long some of this sanding and the cutting would actually take compared to how long it actually did. So like I said, if I could go back, I would probably just put more time, start earlier, put more effort into it, and try to get it done faster and more efficiently than I did.
For me, it would be, if I could go back, I would learn more about the OpenCV library for Python. But if we could, I would like to code in C rather than Python and CV because it's a lot easier, and put more time into it because coding for me is my weak point, but I've learned a lot.
Larger upfront software development and purchase a few of the electronic components. I don't know if that's
So I'd just like to say that I'm really proud of the performance my team has done this semester. I think as a team lead, I would have probably laid down the law a little bit harder, tried to keep us a little bit further on track, but at the same time, since we're all new to this, we're all learning along the way, there's only so much that you can rush, and I'm really, really proud of what we've been able to accomplish.